So today we're talking about protobuf and we're talking about protocol streams. And okay, it's working now. Danny, thank you so much.
Thank you.
All right. This is like, this happens in like almost every single talk. Usually my cables break or my laptop breaks or anything else like that. So it's all good. So again, I'm Scott Haynes. I'm a distinguished software engineer at Nike. I've been working in the Spark community since around 2015. I wrote a book on Spark. I wrote a lot of the Delta Lake Definitive Guide. Also a Databricks Beacon. I was asked to be part of the Beacons program again this year, which is cool. And I teach, I mentor. If people hit me up on LinkedIn with any questions, that's fine. If you're part of the Delta users like Slack group and you have questions, reach out and I will answer any of those questions. All right, over to Ashok.
Hi, I'm Ashok Singamneni, and I'm working as principal engineer at Nike. And I have created two open source projects, Spark Expectations and Brickflow, which we will talk about now today. And I love to teach and help folks and learn.
All right, so moving over. So preparing for the journey. We have a little bit of a kind of compressed timeline for today. So we're gonna get through everything that we possibly can. And if we can't get through other stuff, then I'll just post on like LinkedIn afterwards. So you can have all the source code and everything else to actually have like a reference implementation of everything that we're doing today, which does work and does compile, which is always good. So what are protocol streams? We're gonna go into that. And then how does it simplify data quality? And then we're gonna kind of start going through like the streaming medallion architecture. What does that look like? What does it actually mean? A lot of people probably already understand like about the medallion architecture anyways. So streaming is essentially just making it so that it's just nonstop. Then we talk about like end-to-end trust networks with Spark expectations. So in the same way that we actually have like, high quality ingest of our data, we also want to make sure that we have high quality transformations along in the entire journey from essentially like tin to bronze, from bronze to silver, silver to gold. So moving into ingestion architecture. So the first part of this entire talk is going to be essentially describing the left-hand side of this architectural diagram and going into the right-hand side of this architectural diagram. So on the left, we're talking about protobuf, protocol streams, and something called Buff Connect, which is essentially just a gRPC client. We're talking about edge validations with something called proto-validate, which ensures that any data that we emit from any of our SDKs or clients is exactly what we expect to have before even ingesting it into Kafka, Pulsar, or anything else like that. So we don't have to clean our data. So if anyone's a data engineer in here, you're cleaning data. Things break and you're fixing data. You're spending probably 60 to 70% of your time fixing things that break. This makes sure that that doesn't happen and you can just actually do your job. Then on the right-hand side, we're gonna talk more about like how to actually do like generic applications, how to use protobuf to make sure that generic applications work really well, and then how to actually do a lot of cool stuff with streaming. So moving into it. What is reliable streaming? What are protocol streams? So I could read this verbatim, we just kind of talk about it. So everything's based on protobuf, which has compile time guarantees. It's type safe, and it's been used forever, everywhere. Half the talks you've been to this week have probably talked about protobuf. If you've used Spark Connect, you're using protobuf and gRPC. If you've used Delta Connect, which just came out yesterday, then you're also using gRPC. But the nice thing about it is that you have just that compile time guarantee. So what you compile, what you release, will continue to work, and there's no surprises. All right, so a quick kind of overview of protobuf itself. Protobuf has messages that look a lot like JSON, except they're type safe. And that's really, if nothing else, if we take away nothing else from this, type safety is very important, especially for streaming data. So if things break in stream, you now have a corrupt stream and you have to triage a corrupt stream. If you have data that's really important and it's corrupt, then when you're triaging that, you have no data because it's broken. So protobuf allows us to basically have type safety, but there's other issues along with that.
Yeah, and also we have heard a lot of things about AI and what is the importance of AI and also the data quality that is required for AI to work properly. For us to ingest data properly with all the end-to-end trust networks and have the data properly, we need to have the type-safe validations as well as what protobuf provides us is type-safe and it provides us the way to consistently deliver the data with high quality and also field-level consistency and type checks. And if you see here in the example, we have the bringing field level validation rules where we can actually set up the validation for your timestamp columns, etc., where you will be able to validate the timestamp or any other fields that doesn't rely on that doesn't apply to the type safety checks.
And the really cool thing about this, so Google open source something called like a common expression language, which is Google CEL. So if you take a look at the very bottom, you see like this is less than equal to now. This takes a protobuf timestamp column. if people have worked in streaming data before in different geographies, a lot of times you have collisions with time. And so this is a couple different ways of basically making sure that like we're using like our server as like an arbiter of correct timeliness. So here's an example. If you want to go through the example.
Yep. So if you see the example here, the date 2024-06-13, but the order is created with 2026 date, which is not possible to have. So you'll have an error stated that the validation occurs while you're ingesting the data, and then you will have the error stated that it is not possible to have, and you need to correct the data. So if we are able to restrict the data which is not valid and it is not applying to our validation rules, then at the first stop of your ingestion, you are actually stopping the bad data. That will help us not send the data back into the final layer.
Yeah, and so we always have like these like for sake of examples as well, and it's always just kind of fun to show this. Like the usual use case that pops up in the real world is usually like just because of like a type conversion. So a lot of times you'll have like a long value. You're going to take that into like the JVM. It's going to flip, and you're going to get stuff from the year like 2200. And so if you have stuff from the year 2200, I'm going to be dead by then. We're going to all be dead by then, unless something magical happens, and we can talk about that later. But the big problem is that like when you have extremely like far future timestamps or time traveling, while we're talking about Delta Lake as well, and we have time travel, we just don't want our data to show up in the future until we are in the future. So that really helps a lot. So now we're going to just take a look at like the simplicity of like a client and server side. So if you've ever used gRPC before, or if you've been on like API serving layers or anything else like that, built STGs, built stuff for clients, customers, anything else, this stuff can be really easy. I'm an engineer. I used to write a lot of Java, and there was a lot of like kind of boilerplate and things like that. Like over the years, there's been a lot of things that have helped like with compiling down like really quick like REST services and things like that. But the nice thing, like if you've ever used gRPC before, is you have something called an IDL. So it's an interface definition, and it's an interface definition language. Thank you. I'm like just like sitting here mumbling. But the cool thing with this is that so I've got a message. Let's see if this thing works. It doesn't. We have a laser pointer. It just doesn't really show up. So I've got an order. I expect that I'm not going to actually send data. So I want to require that that data shows up. That's great. Then we know that the data will always show up. If I don't send anything, which happens sometimes with APIs where you get null values or whatever else, that can be bad. In this case, it's just going to basically send back an exception to the actual client, so I don't have to think about it. And so then we just compile things down. So using like the buff CLI, it's just buff lint, buff format, buff generate, and now I have all of my generated code. So like 90% of my day job is done. So moving over there, if we implement the actual service itself, this is essentially like part of like the less than 100 lines of like the entire like actual like service implementation. So I've got a main loop, that's great. I've got an instance of like my proto validator. I've created a service, not surface. I've created a service that actually just sends coffee. So people in here have probably got coffee all week. So you go to get coffee, you create an order, and then you have an order fulfilled because you bought your coffee, and that's great. I work in retail, but coffee is easier, so we don't have to talk about internal Nike stuff. So you buy coffee, and you're a customer of our coffee shop. The cool thing is if I have a validator that just takes a protobuf message, then I can essentially just call validate, and it's either good or not. But I get to compile down my validations. So if you have to worry about like writing all your validation code, always having that up to date with like your APIs, if anything else changes, that's problematic. The other cool thing too is that like we don't have to go into this now, but we can talk about it later because otherwise we'll go through all the time. But if you have like remote modules, or if you're doing like your protobuf in a way where it's like pluggable, you also have the ability to send your validations from like a remote repository. So my service can always just basically pull down latest definitions and always just be in sync with the actual protobuf. So protobuf gets to basically do everything on its own. Whatever domain owns the protobuf can just add its own validations, and the service can actually just implement that. You can also run it locally on Docker. So if you're running like integration tests or anything else before something goes live, then you can just test everything locally. And then that means that everything is valid before it gets into our Kafka topics, which means that there's no data cleansing, which means that we can literally do other cool kind of magic. So we're going to get into that. We'll skip over this just due to time, unless you just want to talk about it. It's like we're sending data.
Yeah, I think we can move forward.
Yeah. We send data, and the data is valid, which is good. So recap, kind of what I was just saying anyways. So protobuf with proto-validate enables high trust ingestion networks. Having a high trust ingestion network means that you don't have to do any data cleansing when you actually start to land your data into like a Delta Lake table, which means that you have good kind of transactional foundational data without having to do anything. The Connect RPC is also a CNCF project, so it's not going away, which is good. Makes ingestion easy breezy. So now we'll move on.
Yeah, and now we have the config-driven applications that are going into the streaming tables and then produce like a stable foundation data tables. But then we have the code ready. How are you going to scale it and deploy it across different regions, different pipelines, etc.? Have you guys used Airflow? How many of you used Airflow before? Everyone, right?
Yay.
We all know the DAGs. Now, if you're using Databricks and we are using workflows, how are you deploying your code? Did anyone try deploying the code at scale in Databricks workflows? Maybe through Terraform, maybe through big long YAML files using Databricks asset bundles. So we had the same problem and we have come up with a solution and we have open sourced that project called Brickflow. It looks similar like Airflow. You can easily write the code, but it works like magic and you can deploy to Databricks workflows. We have a command line utility called Brickflow, and you can just use like brief deploy and you can deploy your workflows. We can show you more in there.
Awesome. So yeah, we'll go through essentially what a generic application looks like, and then what the wrapper for Brickflow looks like around that as well.
Yeah.
For time, we'll just kind of walk through this really quickly. So we talked about cluster by. You heard that in the keynote this morning as well. It's also part of like Delta 3.2, and it's also part of like Delta 4 as well. So if I have tables that are coming in from Kafka, yay, I've got keys, I've got values, I've got partitions, I've got everything else like that. I've also got timestamp columns. As long as we don't have to worry, like we can talk more about like timestamp in Kafka, unless we're actually doing like a retry or anything else like that. Our timestamp is going to be essentially like a source of truth for when we actually ingested something into a broker. So we can do some things where we're basically generating like our dates, which become our cluster partitions, because now we no longer have partitions. But we can generate everything, so we don't have to think about like how to pull stuff out of like our tables. So if you've never used generated columns, it's a really good feature in Delta to do a lot of the work that might just end up being part of a different ETL or a different like phase of transformation. In this case, we can actually do things like this, where we say, take from Kafka, read, do like a nothing selection, and then just write out to our table. And this is essentially what we've called as like it's like the 10 layer of like the Medallion architecture. Yeah. So it's not necessarily bronze yet. Nothing really has happened yet, but all we've done is take our data off of Kafka. Because if you're working with streaming data in Kafka and you have an aggressive like deletion policy, and then you have an outage, then a lot of times you're racing to fix something without breaking more stuff while your data is going to potentially be deleted at the same time. So now in this case, you do absolutely nothing. Because we have our protobuf data living as our value column and it's already been validated, you can essentially just basically time travel later. So fix your problem, go back, replay, and you have an actual good source of truth to go back to. So edge validated protobuf is sitting inside of like our 10 layer. Our 10 layer does nothing. So if you see at the bottom, our value is essentially just bytes. So we've got a byte array. Our key is a byte array. You can do cool things if you're also using protobuf. So your key can actually also contain a lot of other data, because it is still just a good kind of like composite key that stores a lot of other metadata. And so essentially like this is like a reliable landing zone pattern for streaming data, which gives you essentially like a very, very good foundation for anything else you're going to do like within like your data lake.
And then I told you about Brickflow, and we use Databricks asset bundles in the backend for Brickflow. We started off with CDKTF, Cloud Development Kit for Terraform initially, and then we ported to Databricks asset bundles when Databricks have deployed the Databricks asset bundles, and we use the same. But as I said, you will have Airflow-like structure for the workflow creation in your code using Python, but you'll be able to deploy to Databricks workflows. So this is how the code looks like essentially, right? So you have a workflow class where you instantiate, like in Airflow, you have a DAG. So you have a workflow class, and then you have a cluster creation, which you can access, and you can provide the details of your cluster. And then the schedule, quartz expressions, which you can provide. You can add any tags that you want to add to your Databricks workflows, which is customized in the Databricks. And Brickflow also comes with custom tags like the Brickflow version, and also you can automate any tags that you want to add for your organization. And also common task parameters, like in Airflow variables, you want to use common task parameters at the workflow level, you can use those. And you can attach any libraries that you want. We have multiple associations with Maven, Python, Jar, and any other libraries which you want to attach to your workflow, you can add. And there are many other arguments which we didn't put it in this example. You can go through the source code or examples in the repository, and you'll be able to find them. And And this is how, this is an example to create dynamic tasks in using Brickflow, right? You can create a for loop and you can create multiple tasks. Like you have multiple kinds of tables that are coming through protobuf and you are sourcing from different sources. Then you can create different tables using the for loop and you can create tasks. And also you can have dependencies attached. Like if you see the last function where there is a branch, you can have like depends on, and then you can put the dependencies on there. So it uses the decorator pattern at the end. And you can create generic applications using task parameters. And also, cool part is folks who are moving from Airflow to Brickflow, you don't need to forgo all of your operators. You can still use Airflow bash operators or some of the operators that are supported from Airflow. You can still use them in Brickflow as well. So essentially, you have all the things that you need for workflows to work with all the with all the code, but also you are porting some of the operators that you really want from Airflow. For example, you can use operators like Python branch operator. You can bring them and then you can use it.
The other cool thing with that too is that, so I mean, if you're taking a look at like the injection, like where we just have like table, etc. So that's part of like the prior example where we had like the common task parameters. So you can inject that to then create like your generic applications. So everything that you're going to run once, that you're going to then run 100 times, is going to be the same source code anyways, and then you can just automate that whole entire process. So this is also...
Yep, and this is how, after you deploy your code, you can have this command, plug it in your Jenkins or GitHub Actions, and then you'll be able to deploy the workflows. And then this is how your workflow looks like, the source code, what I've shown just before. That results into this workflow, and when it runs, and you will be able to see it. So it actually allows you to scale like thousands of pipelines which you can deploy using Brickflow code like Airflow, but it's very simple. In the backend, it is getting converted into a YAML file, build.yaml, which is Databricks asset bundles file anyways, and we are calling the Databricks asset bundles in the backend.
Awesome. All right. And then the call to action as well.
Yeah, and we are looking for contributors and open for contributions. So if you have any feature requests or if you have any issues, then you can create an issue on the board and feel free to open a PR.
Awesome. All right, so we're moving down over into Schema Medallion Architecture. We're doing good on time as well, so I can like slow down and we can talk more about this as well. So if you hit the QR code, if you want it, there's like the free version of like it's like early release number 5. So this has about, I think it's like 8 chapters of like the full like 16 chapters we have in the book. The book is going to be out in September, but this goes into a lot more detail with a lot better kind of like eloquency than like what I'm going to remember to say on stage as well. Because when you write, there's a lot more time, and when you're on stage, there's a lot of things that you forget. But we're going to talk about internal and external data domains and basically how that improves like the Medallion architecture, but also how that improves like the way that we talk about like, you know, bronze, silver, and gold. Because a lot of people just believe that there's this, you know, oh, my data is going to flow into bronze, then it's going to only flow into silver, and then it's going to only flow into gold. But there's a lot of kind of like patterns where data is going to sit in a specific layer for a lot longer than maybe you think it will. Or maybe stuff never becomes gold because it's never used as an external like domain. And so like the patterns themselves are essentially kind of like it's a way of working, it's a way of thinking that's not necessarily like bound to very strict, you know, buckets. So we're going to talk about that, and we're going to talk about like basically tin to X. So we talked about the tin pattern where all we do is basically do nothing, and we throw data just as raw bytes that's valid protobuf directly into like, you know, a row. Then after that, we're going to walk through like what does it look like to create like consistent like aggregations using a different open source library that we created called Spark Expectations. Well, I should say that Ashok created. I just use stuff. So Schema Medallion Architecture. So we talked about like the tin and the landing zone. And so like this pattern, like we just made something that looked neat for this like, you know, for the presentation. But everywhere we have a table, consider every green box to be a job that's succeeding in like a pretty dynamic, complex workflow. So you think about an internal data domain that encapsulates the optional tin layer. It also encapsulates optional bronze and silver, but there's nothing specifying, like at least like in our diagram, exactly what defines what other than tin. Tin is expected to be nothing. No one should use it outside of like the team that's actually responsible with landing that data, because it's essentially just this raw, you know, basic, like there's almost like no contract other than the protobuf. So people need almost like a PhD level of, you know, understanding of like what that raw data looks like. And a lot of times by the time stuff ends up in like the external data domain or like the gold layer, you know, things are really easy for people to understand. Nowadays, you know, with LLMs, you can just not even have to worry about understanding it either. But like in a traditional world, at least there's some things that you want to do to make sure that people understand the columns and people understand the data. But everything else is essentially like internal. External is the same way that you think about like an external API. So we've got a facade between, and then anything else that needs to be changed for a customer, they never have to think about the internal dynamic network or anything else like that. If you want to change the sources of tables in your internal domain, no one should ever think about that. No one should worry about that because it doesn't matter to them unless they're working directly on that. Tin to X pattern for the Medallion architecture. So if we remember and recall back to like the earlier slides where all we did was basically create like a row that was key, value, timestamp, date, that's pretty boring. There's nothing you can actually do there. We have protobuf because we're sending something from our gRPC client, which is the same proto object. If we use buff, we can basically do make build descriptor, and all that does is it runs bufflint, which makes sure that our protobuf is correct. It generates basically like our AST, and then from there it compiles down the AST so we can basically bring that back into Spark. And so what does that look like? So in this case, the QR code will actually take you to a Jupyter notebook from last year that now has a bunch of stuff from Medallion Architecture. It's called the Hitchhiker's Guide to Delta Lake Streaming. And so here we basically say, we've got native protobuf. We know that we're ingesting that from like our gRPC client, well, from the client to the server and then into Kafka. So all we really need is a reference to a table, and that's a table where our tin table is. We then need a binary descriptor. So at the bottom you see like from protobuf. So this is native as of Spark 3.4. So our data is basically our binary byte column for value. The message name is essentially just like the class path, or it's like the package that we're importing from like our protobuf descriptor. Options is fail fast. If it's corrupt, let's not do anything with it. Let's just fail immediately because something really went wrong. And then binary descriptor set is essentially just like our binary AST. So an AST is essentially like if you think about like a catalyst tree or you think about like print schema on your data frame, it's showing every possibility of what's available from the specific struct. And so in this case, we don't have to think about like managing manual construction of a struct. We pass in a file. Engineers are lazy, and this makes a lot of sense. So this is essentially like what happens once we bring in like the descriptor. All the data that we're passing from like our gRPC clients is already available for us to do anything we want with. We can cherry pick and choose how we actually want to get to any of this data. But we never have to worry about things not existing because it's pre-validated before it even lands. So that makes our lives a lot easier as data engineers. Do you go from here?
Yep. And then we have the consistent extraction from tin to bronze layers, so we can have the transformations done on your buff data, whatever you have got into the layer, and then you can select the data from the data frame, and then you also see the projection there, and it doesn't go into the weeds of it, and it directly has access to the values. So you'll be able to select them and then fetch them, and then you can send the values to the bronze layer.
And the other cool thing too, who in here, when you're doing transformations or anything else, who uses explain? Yes. All right. So explain is going to tell you exactly what's happening behind the scenes. Like what is the underlying Spark engine doing to basically do work? So we saw before a fairly large complex tree. But now here we have a pretty simple like physical plan. And so all this is doing is it's basically doing like memory pointers. So you can basically skip because protobuf already tells us exactly how we can get to our bytes of data. And so from there, there's nothing you have to do. You're not extracting anything else out except for what you need. So you're basically cherry picking in memory without having to ever load anything else into memory. So it's really, really efficient. So if you spend money on jobs, this is a really quick way of not spending money on jobs, which makes everyone happier and you save money and your bonuses and stuff go up. So we have reliable foundational data. So this is essentially just an analogy. So we did tin to X, great. So all that's doing is essentially doing like an extraction. That extraction can be anything we want it to be, because usually it's going to be, somebody has something they need. Our data is going to fulfill that purpose. Otherwise, we shouldn't have that data because there's no one using it. And so usually there's going to be some sort of spec or whatever else for what we want to do with our data. And that's going to, essentially help us define what we want to do with our data as well. So however our aggregations work, we can always go back to like that foundational, like those foundational bytes. A lot of times it's a lot easier for people to not ever have to think about going back to foundational bytes, but they're going to actually go back to a table that's essentially kind of more fit for purpose for them. So in this case, we're relying on our valid protobuf. We're doing some transformations, and these are essentially just here to show you like what's possible with like a streaming query. So we talked about brick flow before, and you need something to be able to orchestrate as you're creating your streaming architecture. So in this case, this is just showing the full transformations.
And then after you have the data into the bronze layer, or the thin layer, and while you are transforming to the final layer, the last section, what we have seen in the overall picture, the gold state, what we have seen, that is a gold layer where the business users will be going to be using the data. But for you to actually provide the data, right data with right data quality, you need to make sure that you have the right data in all the bronze and silver layers. The data has to be propagated. With Proto, we have got the initial validations done. But after that, you would be joining the data with different tables, you would be having your own transformations, but you also need to make sure that the data is with right quality to go to the gold layer. The gold layer can be Genie spaces or the clean rooms or any other models that you want to use, like what we have seen in the talk yesterday and today. So for that, we have built a tool called Spark Expectations. Have you used Great Expectations before? Anyone? Have used Great Expectations? Yeah. And also we have heard of DLT expectations, which is like action-based in pipeline-based, in pipeline, DLT expectations, they will be able to run the data quality and also segregate your data. But this is the answer for the open source Spark projects. Like Spark Expectations is helpful for your Spark, batch, and streaming jobs, where you can actually do action-based data quality, where you are able to segregate the data which is not valid and which is not agreeing to your rules, and then be able to segregate into a separate tables. And we are also able to build different stats, etc. We'll go over the architecture. But Spark Expectations right now will be able to support row level expectations, column and table level aggregations, and also invalid data quarantining. And you will be able to send Slack, email, team notifications, and this is obviously ad hoc and in-flight validation tool. And in here, if you see, there is a table on the left side, and when it is moving through the SE, it is green, but the rest of the stuff, it is pointed as red, because if the data at the first point is not correct, then you are actually transmitting that incorrect data through all the layers, and it will go to the final gold layer, which if you want to correct, then you have to rewrite all the tables from right to left. And correcting the data and rewriting is a pain. Like it takes like a couple of sprints of work and a lot of manual hours and interaction with different teams. But if you are able to restrict that, and if you are able to stop that at the first point, then you will save a lot of time and also effort to actually eradicate that bad data into the final layer.
And so we have in this example, like we're showing so if we had Spark Expectations sitting in a node, then we wouldn't get to like this random question mark of like what just happened, and we wouldn't have all these other problems. And so if we do have Spark Expectations like in the essentially like in the mix, then we can fail the pipeline. So fail the streaming pipeline without having to worry about any of that other kind of quarantining as well.
Yep.
So if you want to go through the error records and stuff.
Yeah. So if you see here, so let's say you have a raw layer, and then you want to take the data into the final layer or the cleanse layer. It can be from bronze to silver or silver to gold. When you are transferring the data, you'll have a Spark Expectations plugged in between, where you are also providing rules table. Rules will have all of your rules, what you want to apply on your data. And then when you plug it into the Spark Expectations does its magic. It's just Spark code, what is running in the backend on your data frame. And after the Spark Expectations, it spits out like 4 tables. 2 are optional and 2 are like mandatory that is given. So one is the error table. Like let's say you have data frame of 100 records, and there are 10 records that is not agreeing to your rules, and you want to drop those records. Then those records will be captured in the error table, where you will be able to go and see the data and then see like why they have failed. You are also having additional metadata information in the error table, where you can go and look at like which rules have failed, why they have failed, all of that information. And then the stats table has your input count, output count, error percentage, and all of that stats information, where you can build a good dashboard for your team. And the stats table can be a global table across your organization, where you can have like big global stats data quality, and you can have like a good nice dashboard out of it. So it has a lot of information that you can dig into with a lot of metadata coming in. And detailed stats table is, it has additional more information on the stats. We just didn't want to plug all of the stats in one table. So we have put certain fields and certain metrics optional, so that teams can figure out like if they want to have it or not. And then the query output is like, if you are running a big query and you want to also store the output of that query to just go and check like what has run, what is my input and what is my output, then that is that information what you can have in that table. That is also optional, because not every team they just want to run the rules, but not want to have all the details stored in a table. So that is why that we have kept it as optional. But after this is run, and all the valid data, only the valid data will go into the cleanse layer based on your rules.
The other nice thing too about the query output, so if you're writing unit tests or anything else like that, and you want to test like that your rules are doing exactly what you want them to do, like if you think about rules just being conditional, kind of like when we were showing proto-validate before, there's certain things that you expect to work. And that's why it's expectations, because it's like, okay, cool, this is what we expect to happen. But sometimes what we expect to happen isn't actually what we write. And so being able to write everything, test the rules before actually going and shipping rules is very good. The other thing too is that like the rules tables, it's just delta tables. So your rules can be shared across the board as well, or you can have localized rules as well if you don't want to share your rules. And this is essentially like also if you think about like, any of the kind of like Lakeview monitoring or anything else like that, here's an open alternative to doing that as well. If you're already paying for Databricks, then this is just a nice thing to have for your unit tests. But if you want to use it and you're not paying for Databricks or you're not paying for those specific features, then you can take all of this same data and still create all your dashboards, plug into Datadog, anything else like that. There's also a Kafka connector for all of like the data to stream back out of the Spark Expectations framework.
Yeah. And then this is how the code looks like, right? So you have a Spark Expectations class initiation in your Spark code, and you can provide the rules table and then the stats table and also the writer. We have written a wrapper on top of the Spark writer so that user can provide the writer information. You like any Spark DF write, you can provide all the options that you want. The default is the Delta format for the Spark Expectations tables in the backend, but you can change them. You can have Iceberg or any format what you want. And then it's a decorator, what you are applying to your function at the end of the day. And you return a data frame on your function. And on top of that data frame, the Spark Expectations will be applied. And then the target table, what you want to write to, you can mention it here. And then you have the user configuration that you can provide, which we didn't provide in the screenshot, but you can go into the source code and you will be able to look at the different configuration parameters. The configurations will have like the Slack notification information, email information, and also the Kafka information. Like these stats, the information, like let's say you have like 100 teams running in and you will have your own permission silos, etc. So we have provided a Kafka connector where you will be able to publish the stats into the Kafka so that you can build one global stats table across, and you will be able to have a dashboard that is built. And what are the kind of validations you'll be able to do with Spark Expectations? There are 3 kinds of validations right now today that Spark Expectations support. One is at row level, which is for every row, you can have like a column definition, like timestamp should be of this format, or any column that you want to have like as a condition, like a predicate condition on SQL, you will be able to put that in a row DQ condition. And aggregation DQ is like sum, min, max, any of the aggregations that you can run at a column that you can add it as an aggregation DQ. And the query DQ is like any referential integrity checks. You want to join with any tables, or maybe you want to check any conditional validations joining multiple tables and check like whether it's a Boolean value, true or false. The output of all of these validations should be a Boolean value. So once you put an expectation like that in any of these 3 validation rules, you'll be able to run any rule that you want on your data frame. And what are the kind of actions you can do with these rules? Let's say your rule is not satisfied. Then what do you want to do with that rule? If the data is not agreeing to the rule what you have said, you have given, then you can either ignore it, but still record it in your error table, or you can drop the record, or you can fail the job. So these are the 3 actions that you can call for any rule in Spark Expectations. And when you do that, you'll have the clean data in your final table. At least the data what you want and agreeing to your rules. The rules are always modifiable, and you can always do iterations, and you can start off small and then you can take it from there.
The other nice thing too is that because the rules are part of like an external table, your jobs don't have to change. The rules table can change. You can rerun your job to fix things that should have worked, but maybe weren't actually correctly done. So it's not like you have to recompile or do anything else like that as well. So it's basically just like a pluggable rules table.
Yeah.
And so this is essentially like the end result of using Spark Expectations, like where before we'd had bad data that basically trickled all the way down and creates like that costly problem where you have essentially like every upstream is like, well, what's happening upstream from me? I don't know where this problem actually started. Instead, you basically block it and you can fail before everything actually starts to trickle downstream. And like as you have like larger and larger number of tables that depend on other kind of upstream tables, or the more you kind of get into like single sources of data truth, like the more you need something like this anyways. Otherwise, all you're going to be doing is essentially trying to triage problems, and then that takes more and more like more brain drain and everything else like that. and then usually people quit. So we want this to be essentially like we block, we fix, and then the second we fix, the rest of our jobs can continue to run. And so this is like the perfect world, the North Star that people want to kind of live in. It's just usually not that way when you're working in like a typical enterprise or even just any kind of company in general. Data is hard.
Yep. And then we are creating the rules right now in CSV files or YAML files or writing the rules manually into the tables. We wanted to build a UI-based rules engine where you can actually, where business people and technical analysts and anyone who want to write the rules, they'll be able to write the rules using a UI. We just started off the project for the UI in Spark Expectations open source project. So we are calling for collaboration where the backend of this UI, interesting thing is that it will be GitHub. The rules will be managed and maintained in GitHub and versioned, and you can raise a PR directly from the UI so that a PR will be raised and folks can review the rules, what has been applied, and it can be versioned, not as a database, because if we use a database, then if we want to propagate to different environments, dev, QA, and prod, it's going to be difficult. So that's why we decided to have a GitHub as a UI for this so that you can integrate that with GitHub or Bitbucket, whatever you have in the backend, and you will be able to manage the rules. So this is the current state of that project right now. But I think we'll be releasing a version soon for the UI, and we are looking for collaborators. And thank you.
Awesome. So yeah, we've got like a minute left. So essentially, reach out on LinkedIn, find us anywhere online. We've got a lot of different projects. Nike's re-entering the open source world and doing a lot more stuff now as well. And yeah, that's pretty much it. So we've got a minute left. If there's any other questions and people want to actually ask those questions, feel free to ask them now or just come up and we can just call it a close as well. So thank you, everybody.
Thank you.